Hi everyone, my name's Orion Rust. I'm a physics tutor here at BYU Continuing Education, and today I'm going to be going over the infamous incline problem. Now, inclines appear super often in both high school and university level courses. So today we're going to walk through some incline problems, basic strategies, and how we can go through them. So typically we're given an incline and which is conveniently in the shape of a right triangle. And we have a point mass sitting on this incline. And usually it's accelerating in one direction or another. For this example, um, we'll have it accelerate in this direction, in the downward direction. But sometimes if you apply a force in the opposite direction, it can also accelerate up the incline, depending on how you do things. But for this example, we'll pretend like there's no other force acting on it other than the force of gravity, the force of friction, and the normal force. Let's draw a free body diagram right here, just to get ourselves sorted out. So starting with the force of gravity is almost always downward, and unless you're in space or something goofy. But we assume for most systems that they're on planet Earth. And so we have our force of gravity. And as we know, our force of gravity is simply the mass of the object times the acceleration due to gravity, which is um, 9 point, oops, which is 9.81 meters per second. Now, because the force of gravity, it almost always accelerates downwards, we're just kind of concerned in this instance about the magnitude of the force of gravity, so we tend to draw it like this. But in certain circumstances, especially with kinematics, if you have an object that's launching, you want to make sure that our g is negative, because that will make a big difference. But for dynamics and equations like this, it doesn't make too big of a difference. We're more concerned about magnitude in this instance. And there's a lot of hand wavy mathematics that we're going to do, but it'll mostly make sense for the most part. So we have our free body diagram. We have our force of gravity pointing down, mass times acceleration due to gravity. Then, because we're on an incline, we want to draw the rest of the forces in terms of um, a new x and y axis according to the incline. So we take our normal incline that we have and we tilt it theta degrees. Um, we have this new axis, and this is how we're going to operate and describe the forces. Now, I know it sounds kind of funky right now. Just hold on with me, and it'll all make sense in a second. So let's start with forces that are acting on the x direction. In the x direction, um, we have we have the force of friction. Um, it's only if they tell you that there is no force of friction that you can ignore the force of friction. But more often than not, you'll have the force of friction thrown into the mix. And the force of friction always goes opposite the direction of motion. That's our resistance. And our force of friction, if we write out our equation, is equal to mu, which is our coefficient of friction, and the normal force. Well, what the heck is the normal force? The normal force is the balancing force that makes up for things using Newton's third law. So the normal force in this instance is going to be perpendicular to the incline. The normal force will be pointing perpendicular to the incline. Because think about it. If the box is if the box is going this way, if in the y direction, according to our new x-axis, if there was only a force pointing downwards, what would happen? The incline would crumple, right? What's holding the box on the incline is the force of the incline on the box, which is weird to think about. But according to Newton's third law, every force must have an equal and opposite force. And that's essentially what our normal force is. So our normal force, we usually represent it with a big capital letter N. You could also see it described as F sub N, or there's lots of ways of writing it, but it's most commonly you'll see it in high school and especially in university by the big letter N. But wait a minute. Why is the normal force a lot smaller than the force of gravity? The force of gravity as we have it right now is not in line with our new X and Y axis. It's at its own angle. It's doing its own thing. And it's really not much use to us. So what we're going to have to do in order to solve this problem is compartmentalize the force of gravity into the parallel and the perpendicular, wow, I can't speak English, the perpendicular directions. So let's draw these dotted lines. Now, these aren't actual forces, but they describe parts of the forces. So we'll write this one as the force of gravity perpendicular because it's perpendicular to the incline. It's at exactly 90 degrees with the incline. As you can see, this one lines up with our y-axis, and it makes sense. And our force of gravity perpendicular is going to be equal to the normal force. We'll write this, let's write it up here so that we can have it a little bit closer to where it is. Fg perpendicular is equal to the normal force. Think about it, because the sum of all the forces, now if you're in high school, you probably get a heart attack when you see this symbol. Don't worry about this. This just means the sum of all forces. You could also write it as F net, or all the net force. The sum of all the forces in the y direction, and we're not talking about the regular y, we're talking about our y adapted to our angle theta, is zero. It's not accelerating in the y direction. The box isn't floating off the incline, or it's not crumpling into the incline. It's staying steady. Even though it can be moving in the x direction, there's no movement. So it means the forces are zero, which means that um, Fg perpendicular minus the normal force is equal to zero. So therefore, we can say that Fg perpendicular is equal to the normal force. That's kind of how we got that. Does that make sense? If it's not making sense, pause for a minute and think about it. Why this makes physical sense, and why the force of gravity perpendicular is equal to the normal force. Now, this isn't the only component of the force of gravity that's important. We also care about the force of gravity parallel. Now, this is the force of gravity, the parallel component is what is pushing that box down the incline. It's what's pushing the box down the incline. Or when you're on a bike and going down a hill, your gravity is pushing you downwards. Now, the force of gravity itself is pushing downwards, but it's the component. If you take a component of that, um, the parallel component of your gravity is really what's doing the work. And it's interesting, your perpendicular component of gravity will actually affect your friction because the normal force is equal to the perpendicular force of gravity. Think about it. The harder you push down, the harder the force that pushes against you um, is pushing upwards. That's why when part of the physics of running is when you put your feet down, you exert a force, and the harder you push, the harder the ground pushes back up at you. I know it's weird to think about it, but that's Newton's third law, right? Is that there's an equal and opposite force in everything. And so our force of friction, we can also write it in terms of the force of gravity perpendicular. And this is actually going to be really, really important because the force of friction is on the x-axis. So we're using the force of gravity perpendicular, which is on the y-axis, to describe a force on the x-axis or our new x-axis that we've made. Think about it physically, right? The heavier you are or the more mass that you have, the more, the greater the force of gravity, the greater you push down on the ground. Or In this instance, it's not quite the ground, it's the incline. That's our surface. Whatever surface you're on, the harder you push down on the surface, the harder the surface is going to push back on you. And so that also means that the force of friction is going to be greater the more mass that you have, which is our resistance to motion. So how do we do this? How do we go about finding these values? We're going to draw a triangle. Now, we'll do a little bit of hand wavy math. If you talk to a mathematician, they won't be too happy about this, but physicists and engineers are chill like this. So let's take, we already have a right angle right here between the force of gravity parallel and the force of gravity perpendicular. We're going to slide this force of gravity. Just imagine it sliding down here and forming another triangle. We'll draw this triangle down here. Um, this is our force of gravity, which we can write in a more calculable way, mg. Then right here, we have our force of gravity perpendicular. Then right here, we have our force of gravity parallel. So we have this cute little triangle right here that's going to help us solve our equation. And we can describe these things using trigonometry. Now, this is a blast from the past, back to ninth and 10th grade geometry. We have SOHCAHTOA. SOHCAHTOA. Now, essentially, we're going to describe the force of gravity in terms of the regular force of gravity. We're going to describe these compartmentalized versions of the force of gravity in terms of regular plain old mg. So let's start with, before we go in, does that make sense? Just imagine this triangle that we drew. Kind of, we have this triangle right here. Let me see if I can do a triangle with my hands. We have it, and then we just kind of flipped it on its side to match with these new forces. And it makes sense. Just imagine like it, we flip it along this axis of rotation, um, and we shrink it down a little bit. Now, this isn't very mathematical. This isn't actually correct at all, but well, we're doing physics, so we can be a little loose with it. We can be do some hand wavy mathematics and say, yeah, it works out. We don't need to do some geometric proofs. Those days are over. They're behind us. You're okay. You're in a safe place now. Um, just a little slightly more safe, and we're doing some physics. So, um, using our right triangle laws, the across from the right angle is the hypotenuse, which is our h. Um, and our opposite angle theta is our O. And the other one that we have left is adjacent because it's right next to the angle, and it's not the hypotenuse, and it's not the opposite. So if we want to find um, our FG parallel, what trigonometric equation would we use? I'll give you a second to pause and think about it. Which trigonometric equation describes FG parallel and MG? That sounds a lot like cosine. So we write cosine theta is equal to FG perpendicular over MG. And because we want to solve for the perpendicular force of gravity, we get F, let me start over. That was pretty sad. FG is equal to mg cosine theta. Perfect. So this is our perpendicular force of gravity, and this is they could ask you for this on a test. More often than not, they're going to ask you for the acceleration um, of the block itself. You'll usually be given the mass of the object, you'll usually be given the coefficient of friction, and um, you will also usually be given um, the force of gravity and theta, the angle that the incline makes with the ground. These are our givens. They're usually some value. You can have the mass be like 2.1 or something, or 0.25. We already know G is 9.81, and theta could be like 27 degrees. And so we have these givens, and all we need to do is make an equation um, in terms of whatever we're asked for in terms of these givens. Then we could just plug it in. Now it's making the equation that's a hard part. And once you plug things in, if you know how to use a calculator, if you're above kindergarten level intelligence, it should be smooth sailing from there. So let's go to our force of gravity parallel. Now this is going to be significant because remember, this is our in our x direction. Um, and we don't have acceleration in our y direction, but we do have acceleration in our x direction. More often than not, you're going to be asked for an equation. You're going to be asked about the acceleration um, of the system. And because we are accelerating in the x direction, that's going to be the only thing that really matters. So, what operation can we use that involves both FG parallel and MG? That's right. If you said sine theta, give yourself a pat on the back. If not, that's okay. We all have to start somewhere when learning physics. So we have sine theta equals FG parallel. Let me start over. FG. Oh my gosh, it's so hard to draw with a mouse. FG parallel. Hope you can read my chicken scratch, which is um, so essentially we can multiply mg by both sides to algebraically manipulate the equation to get it to a place where we like it. It's going to be fg parallel equals mg sine theta. Now, why do we even care about this? Because this helps us dissect the force of gravity in terms that are applicable to this axis. If we just have the plain old FG, we can't really do much with it. We can't really have it, we don't know how it relates to our N or our force of friction until we have these equations. These help us understand the force of gravity. Now, a lot of the times we're tempted to think, oh, it's just plain old cosine. We can relate it to x. That's the typical thing in mathematics is cosine relates to the x direction and sine relates to the y direction. But with this, we see it's actually the opposite. With our y-axis, we have mg cosine theta, and with our x-axis, we have mg sine theta. So with equations like this, it's super easy to go on a shortcut. But instead of jumping to conclusions, make sure and check yourself before you Shrek yourself. So it's super important that you check yourself and you draw out a triangle like we did here. This is all part of the process. So let's do, given what we've been given so far, we know that the sum of all the forces in the y direction is 0. So what we know is that um, the force of friction, excuse me, the the normal force is equal to um, the perpendicular force of gravity. So we can bring this equation that we have over here, and we can write it as the normal force is equal to mg cosine theta. Now, why do we care about this? Because it translates to a force directly in the x direction. Because we established earlier that the force of friction is mu times the force of gravity parallel, we can also say in this beautiful equation, the force of friction is equal to mu mg cosine theta. Now, what is this telling us? The force of friction, the magnitude of the force of friction is going to be the coefficient of friction, mu, times the mass, times the accelerational gravitation, um, the accelerational gravitational constant, which is essentially the force of gravity, at cosine theta, the angle. This is telling us the magnitude of the force of friction. It's in relation to the force of gravity. It's basically the force of gravity in the perpendicular direction times the coefficient of friction. This is going to be important. We'll kind of store it in our minds and think about it later. In the x direction, we have sum of all the forces in the x direction. Now this is not equal to zero. We have acceleration in the x direction. It's completely still in the y direction, not moving up or down, but it is moving down the incline. So we're going to use Newton's second law and write mm, the sum of all the forces is equal to mass and acceleration. In this instance, it's in the x direction. We don't need to note it, but it's good to know that this is going to be the acceleration in the x direction. So what do? We write out the sum of all the forces. MA is equal to, what are all the forces that are acting on the box in the x direction? Let's see. We have the force of friction is acting opposite to the direction of motion, and we have the force of gravity parallel. We established that we know that FG parallel is going down the incline. And for this, we'll assume that going down the incline means positive acceleration. Now, if they tell you on the test it means negative acceleration, you put a minus sign in front of it. Um, and you do the opposite for the opposite force. So if the acceleration for some reason is negative, you can add the force of friction because it will be going in the positive direction. But more often than not, it's going to be it's going to be the positive direction that's down the incline. Um, and so you can write FG parallel as positive. And the force of friction is pointing up the incline in this direction. And because it's going the opposite direction, we need to make sure that it's subtracting. So we write our equation like this. Now what we can do is we can substitute these values that are at first arbitrary numbers. We can make them into values that we can use and plug in. MA equals force of gravity parallel. We established this down here is mg sine theta. We subtract the force of friction, which is mu, the coefficient of friction. We have our answer down here. Mu mg cosine theta. And now we want to solve for acceleration. So something cool that we can do is we can divide all sides by m. And what happens? All the m's cancel out. Now this is pretty cool. What does this tell us about mass? We write our new equation. There's not an m to be found at all. We write it g sine theta minus mu g cosine theta. So the value of m doesn't really matter. Because think about it physically. If you have a greater mass, there's going to be a greater force of gravity pushing down. The greater the force of gravity pushing down, the greater the friction. And what it's telling us is if you increase the force of gravity, if you increase the mass by a certain amount, the force of friction will increase by that same amount. So that force of gravity that's parallel, that's pulling it down, will also the force of friction, because of the normal force, or the force of gravity that's perpendicular, it'll increase the same amount at the same time and push back the same amount by the same quantity of mass that it increased. Does that make sense physically? Think about it in your mind. If you have a small box, um, it goes down at a certain acceleration. If you increase the mass of the box, in this instance, the way that we have it set up, mass doesn't matter. If you increase the mass of that box, the force of friction on the mass of that box and the force of gravity parallel that's pulling on it will increase at the same magnitude. They'll increase by the same amount. But that's not it makes sense for this instance, but it's not going to be the rule for in general. So you want to be careful and run your equations like this. Now we have our answer. Um, our acceleration is described in the terms that were given. We can double check and make sure that we have all these terms before we plug them in. Um, it's the acceleration due to gravity times sine theta minus the coefficient of friction times the acceleration due to gravity times cosine theta. So this is awesome. What we did is we essentially took these values that were kind of arbitrary and had no meaning, and we described them in a way that we can plug them in with real values and make sense of them. So just to summarize what we did, a step-by-step process. We drew out our incline. It helps us a ton to just visualize things and get a sense. We drew the direction of motion, and it's usually positive down the incline, unless you're told otherwise. We thought of things in our new axis. We rotated our x and y axes by theta degrees, and we drew a free body diagram with all of our forces. We also drew in the components with dotted lines, FG parallel and FG perpendicular. And we established some things that the force of gravity perpendicular is equal to the normal force because there's zero acceleration in the y direction. Um, in order to solve the problem, we drew a mini triangle with the components of the forces um, in their correct places. And we drew a triangle that's essentially just a flipped version of our incline. And on it, we used some trigonometric properties to derive these equations. And these equations are useful because they're in terms of our givens or what we already have. We then used Newton's second law to find out the acceleration in the y direction. It's zero. Um, the normal force is equal to force of gravity perpendicular, which is mg cosine theta. And we plugged it in to find the force of friction, which is described as mu times the normal force. We also found the sum of all forces in the x direction. Because it's a non-zero acceleration, we write it as F net, or the net force in the x direction, is equal to ma. And we plugged in these values. Those are the two forces that are operating in our x direction. And it's Fg minus the force of friction because the force of friction works against it. We canceled out all our m's and found out that the mass doesn't matter, and we got our answer. Acceleration is equal to g sine theta minus mu g cosine theta. Now, a lot of the times, sometimes they'll ask you for the velocity. How the heck do we do that? Just basic kinematics. We have our handy dandy A equals delta V over delta T. Um, if you feel like reviewing some kinematics, I also uploaded some kinematics videos, so feel free to check those out and review those, but it should be pretty easy going from there. Anyways, hope you enjoyed. I hope you learned something, and best of luck on whatever test or class you're preparing for. Or if you're just watching these videos for fun, you're kind of a nerd, but that's awesome. I really respect you for it. Anyways, thanks so much for watching. Till next time.